Okay, so in this last lecture on the quantum field theory, we're going to talk about the Dirac Sea. So in the previous lecture, we were able to look at the vacuum expectation value of bosons by thinking about what happens if we had two parallel plates. For the Dirac Sea, we have to do something a little bit different to that. If we want to know that this Dirac Sea is physically there, we have to push on it somehow. We have to give it some kind of force. We can't give it a metal plate anymore, but what we can do is we can apply a magnetic field. So we'll start by calculating the Landau energy of the Dirac Sea with the uniform magnetic field applied. So the first thing that we need to do, and I'm just going to bring this one from the sky, is look at the Landau spectrum. So the Landau spectrum for Dirac particles is written as energy equals plus or minus square root m squared plus p squared. So we quantize it in the z direction. So the magnetic field is in the z direction, and you can actually generate this formula just directly from the non-relativistic case by changing the Dirac equation formula in the magnetic field so that it kind of matches with the non-relativistic case. Oh, and I need a density of states as well. And that again comes from the non-relativistic formula. Number of states per volume is EB over 2 pi squared times PZ. So if you don't remember this, these formulas, just go and look it up in the textbook on non-relativistic quantum mechanics, because that's actually all we need. And there's a slight modification for the fact that they're Dirac. For example, the energy can be positive or negative. But if you look at the non-relativistic formula, you'll see something that looks very similar to this, and you'll be easily convinced. So that's the spectrum for the particles. So then we want to know, well, what's the total energy of the Dirac Sea per unit volume? And you remember the Dirac Sea is made up of all the completely filled negative energy states that are in the Dirac equation. I'm also going to take a little bit of a liberty and just start writing the absolute values of E as E itself, because I'm going to get real bored of writing absolute value of E all the time. So we have to sum up over the entire Dirac Sea. So that's states from n equals 0 to infinity, and S equals plus or minus 1/2 of E B over 2 pi squared square root m squared plus pz squared plus omega. Okay, and yeah, so that's where I should have the absolute value of E there. I've just got E itself. But if I keep that absolute value, it will get a bit crowded. Okay, now if I look at this thing, it's clearly infinite, as it should be. It's a infinite set of particles filled up, so it's an infinite sea of particles. All the Landau levels are filled, all the spin projections are filled. This is infinite. And now what I'm going to do is I'm going to regularize this somehow and make the infinities removable. So I'm going to change colors, and if you want to skip ahead, you can just scrub ahead until you see me go back to black, and then you'll know I'm done with the regularization process. If you want to watch the mathematical details, then keep watching. So the first thing to do is I'm going to take the derivative with respect to m. For Casimir, I actually ended up taking an integral, but this one will work out for us. Now that I've written the limits of the integral, I don't have to write it out every single time. So now I've got the mass term on the denominator, and now I want to regularize this with a standard integral. So that's a standard integral that we can use here with x equal to what's in the surd on the denominator there. That means I will get, and so this t is a dummy variable which we introduced just in order to be able to do the integral. And now each one of the terms here I can actually do separately. So the first one is that I can do the sum over n equals 0 to infinity of e to the minus 2eb Tn. So that's one of the terms there that you can see. That's just a geometric series. So that's equal to 1 over 1 minus e to the minus 2 ebt, where the n goes away because that's the exponent in my geometric series. Similarly, I can do the term in S. It's a little bit less dramatic. And I can do the integral over P as well. Sorry, that should have been dp, obviously. And that integral is simply take that part out, and the integral of minus p squared times t, it's a standard integral that we all know from first year or second year, and it's square root pi over square root t. So putting all that together, we get, okay, so the coth is just, you can see these factors e to the power of TEB coming around, and so that's what ends up being inside the integrand. And now we're nearly there, actually. So now I integrate over m again, and so then I'll get welcome back to everybody who got bored of the mathematics. You probably came back too soon, actually. Okay. Now, for large T, coth tends towards 1, and the exponential term will make the integrand die away. So at large T, this converges nicely. For small t, there's a problem because we're going to have a 1 over t squared divergence. So in order to do a small t, where that exponential decay hasn't kicked in yet, we are going to have to do integral from naught, and so we'll go from, the integral from naught to infinity, but really the upper limit will be, of order 1 over m squared. That's the t that we have to kind of get to before the exponential will kick in for us and help us out. And so what I'll do is I'll make these small EBT expansion for the coth. And just a reminder again that this is the absolute value of E in the denominator here. It's very important later on. And so I'm expanding out the coth. These are the first few terms. I don't remember these, I just looked it up in Mathematica. This order t to the power of 5 here. And in this case, because we're looking at very small values of t, I have ignored the exponential. So when I look at this integral, I see that the first term and the second term both diverge for small values of t. They both lead to the infinities. The first one goes as 1 over t cubed, and the second term goes as, so when I integrate it will be 1 over t squared. The second term is 1 over t, so when I integrate that, it's going to go as log t. And so as t goes towards 0, they're both going to diverge. So in order to renormalize my energy density, I need to remove the first two terms from the coth function. And so this is my final integral. It's still expressed as an integral, but now it's finite and it's useful, and we can see that it's well behaved. So we could actually take this integral and evaluate it numerically. For us, however, we just want to know a few things about it, like what does it look like in the weak field limit, what does it look like on the strong field limit, and so on. But in general, we've kind of gotten a solution now. It's not in a closed form, but it's something which is useful. What we'd now like to do is get the weak field limit, lowest order in magnetic field B. Well, in order to get the weak field limit, all I need to do is expand out the coth and just keep the first term, which has not been killed away by the renormalization procedure. And for that, I then end up with, and let me restore the absolute value of B, of E rather, just to make sure that we know. It's EB over 4 over 360 pi squared m to the 4. So all I've done is take the EB over 8 pi squared, which is outside the integral. If we look at the coth, it's EBT cubed over 45. So that's why we get this factor of 360 here. And so we can see that the energy density here goes as b to the power of 4. Now remember, in Maxwell's equation, it went as b squared. So we do not expect it to go as b squared. If it was a b squared dependence, then it should have already been included in Maxwell's equations, right? Either by a modification of our definition of charge, or alternatively, we would have gone, oh, well, Maxwell's equation is no good at all, and they never would have been written down. So it would have been noticed and would have turned up in the original theory, but because it was a higher order in the magnetic field, at low magnetic fields, it's a good approximation to have the energy density going as b squared. So the next question we might ask is, well, what's the scale that we do have to worry about this magnetic field? So let's write that out. And I think that this was Schwinger who wrote this down in the 1940s. So that's the scale that you can no longer ignore QED effects. If I write that down in Gaussian units, it's m squared c cubed over e h bar. That's Gaussian. Or in SI units, and that comes out to something like 4.4 times 10 to the power of 9 Teslas. And so I can write for magnetic field B, if I write it in terms of BQED, in other words, we can rescale the magnetic field to the kind of natural scale for this problem, then I would write here that the energy density is minus m to the 4 over 360 pi squared b to the power of 4. And that's only true when b is much smaller than 1 in the weak field limits. Okay. Next, let's do the strong field limit. So let's write x is defined as EBT. And so we can write dE, that the energy density is and the first term that I have to keep, if we just go back up to our equation here, we can see that we're looking at this one at the top here. The Koth term, for large B, this Koth term will tend towards 1, because for large B, Koth tends towards 1. For large X, Koth X tends towards 1. The second term here is 1 over EBT, so that one will tend towards 0 for large B. And the third term, as B gets to a large value, that term is going to go as B itself. And so in fact, out of those three, it's the last one which has the largest effect. So we can write here minus x over 3. Okay, now I need to solve this integral somehow. So the integral, so firstly, it's at large x values. And so I don't have to worry about the small x values. And what I need to do instead is I need to think about the integral, and maybe I'll do this in a different color as well. So what I'm interested in is the integral from naught, rather incorrect, from 1 to infinity, because it's the large x values that I'm worried about. Dx on x, e to the minus x over b. And the way to think about this is that you've just got an integral of 1 over x, but at some point that exponential kick in, right? So b is a very large value. So when x gets large of order b, then the exponential kicks in and goes down faster than 1 on x. So the way to think of that is you've got an integral that looks like 1 over x, like this. And then at some point, that exponential comes in, and it's like a cutoff because it falls down faster. So the exponential doesn't do much when x over b is a small value, but it does a lot when x over b is a large value, and it cuts off this 1 over x. And so I can think of this integral as being the integral from 1 to some cutoff, and the cutoff will be at around b of dx on x, and that is just log of x, so it's log of b. And so that's actually a good approximation for our integral. And so what we get in the end is we get the energy density is approximately equal to so this is 8 pi times the 1/3 that's come through. 1 over 8 pi times 1 over a third. So 1 over 8 pi squared times a third. Getting it right eventually. And this integral, it should have a minus sign here as well. And it should have this log of e b over m squared, or minus m squared over, sorry, that should be m to the 4. Minus m to the 4 over 24 pi squared b squared log b. Okay, and so that's the large field limit being much, much bigger than 1. The strong field limit. Okay, and that's quite common as well in these kind of field theories, is that you get a logarithmic, well, in the strong field limit you'll get a large log. So in principle we could repeat the kind of analysis we've just done for the uniform magnetic field, except to have a uniform electric field. But in fact, it's kind of not that easy. So what we're going to do is we're going to cheat. So what we'll do, imagine traveling at high speed through a homogeneous magnetic field. So there's our magnetic field, and imagine that you are cycling through it very fast. I always like to think about bicycles. But you're in a very high-speed bicycle today, going through this magnetic field. What do you observe? You'll notice that the B field appears weaker than it is to the ground-based observer. And you will also notice that there is now an E field. And of course, we know that because that's the basis for Lorentz boosts of electric and magnetic fields. The Lorentz invariant is E squared minus B squared. Right? So in your Lagrangians, you've always got things like, 1/2 E squared minus B squared, or 1/2 B squared minus E squared, or something like that, or 1/4 F mu nu, F mu nu, so that ends up being the same thing. So this is the Lorentz invariant. And so what happens is, in the fast moving limits, you won't see a magnetic field anymore. That will go to 0, and instead you'll only see the electric field. And so you can see that you'll make a transformation from B field to IE. And it could be minus IE as well. Either way, it doesn't really matter. So what we're going to do is we're going to make this transformation to the renormalized energy density of the Dirac Sea in the uniform magnetic field that we already know. And this transformation simply looks pretty much the same as it does for the magnetic field, but we need to worry about the factors of I, and in particular coth of IE is I cot. So it goes from coth to cotangent, EET. And notice that this last term has changed sign. That's because it gets an I squared. And you can run this cot minus 1 over this part that's in the square brackets here, you can run that through Mathematica, for example, and just check that it's still convergent at low values of E. It is. The next thing we want to do is have a look at the weak field and strong field limits. Just for the small field limit, it's going to be fine. It's super easy. For the high field limit, it's a little bit more difficult because the COT has all of these divergences, right? As E keeps growing, you end up, COT goes through infinity and then it goes to minus infinity, infinity, minus infinity. And when you integrate over that, it becomes a little bit complicated. The total integral is still finite, but it just gets more complex to evaluate the integral. What we do instead of that is we can just go and directly change the limits from the electric field, from the magnetic field case to the electric field. And so since I've cheated this far already, we can just write A equals E over E QED, which is M squared over E, just like B QED. And so we'll take from our equations where we've gone B goes to IE, we're now taking this B goes to IA. And that means that we will get for our limits, we'll get minus m to the 4 over 360 pi squared, a to the power of 4. That's for a much, much less than 1. But in the strong field limits, we get something a little bit interesting. M to the 4 over 24 pi squared. And now that I squared comes in, and so now it goes from being negative to being positive. And we've used, because we have the logarithm of IA, so we had to take the logarithm in the complex plane. And usually we write something like the logarithm of a absolute value plus I times the argument of A. And I'm not really interested in the argument today. I should write that with a capital L as well in the standard complex notation. So I should have written we have used as well. And that's interesting because that means that the sign of the strong field limit is positive now. So that means that the larger the larger the field is, the larger the energy density is, and so that has some manifestations as well. One way of kind of thinking about this strong field limit is imagine that we create a very large electric field, like magnitude E much bigger than EQED. Then I could add back in the Maxwelly part of the energy density. So the Maxwelly part is E squared over 8 pi in Gauss units. I think it's the same in, you need epsilon noughts if you're in SI units. So in Gauss units, it's E squared over 8 pi. And now we can add to that the QED part. Something like this. And so if I take out the normal bit, the Maxwell part, then I'll get 1 plus. Okay, so imagine we have a field that's like I don't know, like 1 or 2 orders of magnitude larger than QED, then the size of the logarithm, log E over EQED, will be of order, I don't know, 3, let's say. Yeah? I mean, because it's logarithm, it only grows slowly. So 3 will be kind of a typical value if you're just a little bit bigger than EQED. And it's hard to make it much larger than that. So it's a kind of a smallish unitary kind of value. One way of thinking about this is that the action of the Dirac Sea, or the existence of the Dirac Sea, I like that better, increases the energy density by order of a few percent. So I don't know, what's that, 0.3% or something like this, right? So it's kind of large. Like that feels like something that you'd be able to measure. Of course, getting in the electric field that is that large is quite difficult. But actually, there are certain points where it's not that difficult, and that's, for example, close to a nucleus. Because even though the charge of the nucleus may be fairly small, we can get very, very, very close to it with our test particle, with our electron. So the question is, how close do I have to get to this nucleus in order to start seeing these QED effects? So I need my electric field, which is E squared over R squared, ZE squared over R squared, to be approximately the same as E times EQED, and that will happen when we have R squared equals ZE squared over 4 pi M squared. So that gives us a kind of a value for how close we have to get. Okay, and then you say that when the electron is close to the nucleus, its effective charge will increase. So if you have a look at how the field works, it just increases the energy density, but another way of thinking of it is that it increases the effective charge. E tilde squared it's like the regular charge, but it's increased by that factor that we saw before. 1 over 3 pi times some large logarithm. Large logarithm, 3. And then what we want to do, we want to think about, okay, what is this large logarithm doing? So E over M squared is now Z alpha over R squared M squared. And that's the logarithm of Z alpha. Well, that's not very interesting, that bit. And then I'll write minus 2 log of Rm. So I can write that as Rc over R. Make that a plus, where Rc is equal to 1 over m. So define Rc like this. And so Rc 1 over m, that's the Compton radius of the electron. So now we understand, so that when R is much, much less than Rc, so when we're well within the Compton radius of the nucleus, the electron will see this increased charge. And so then we would write, so the Compton radius for the electron is like, 1/200 times the Bohr radius, roughly. So, this is not a tiny, tiny effect. And what happens, it says that when the electron is close to the nucleus, that the electric potential is a little bit deeper. So the electron sees a deeper Coulomb potential. And so it's not just 1/r², it's now seeing something much deeper in that a deeper force. And so this is quite interesting, because you would think, and by the way, the log Z alpha doesn't matter too much, because it's constant in R, and we can sort of neglect it in the same way. Well, we also neglected a term that was similar to that when we made the original strong field limit for the magnetic field, right? We just took away the part of the integral between 0 and 1. So this is kind of similar to that. So we have this limit, and when you see something like this, you'd think, well, surely that would have been noticed already. I mean, you can do a hydrogen-like system and you can see this effect. And in fact, you can. It's part of the Landau shift. And so this is called the vacuum polarization. And what it does is it will take the Dirac equation that looks like has degenerate levels for 2s and 2p1/2, right? We studied that before. And it will split them. The 2p will be almost unchanged. Why? Because that one has a centripetal barrier which stops it from coming towards the nucleus or getting too close to the nucleus, and stops it from feeling that extra potential. The S wave has no centripetal barrier, and so it will feel a deeper potential. And this would be an excellent explanation for the Landau shift. Which had actually been noticed already in the 1940s. But it's not. And that's because the ordering of the levels is the wrong way around. So you can see this effect, but there are other effects which dominate. That's the self-energy, which is another QED effect. And it turns out that it actually switches the order so that observed Landau shift is actually the other way around. So the vacuum polarization is part of it, but it's not the whole story. And so what you actually see is a splitting that goes in the other direction, where the 2p1/2 is lower than 2s1/2. Okay, but that one's more complicated and we won't talk about it anymore. So that's probably a good place to stop. We've shown that you can elucidate the nature of the Dirac Sea by pushing on it with a magnetic field, and then you can work out what happens in an electric field, and then you can say, hey, we should be able to see this in atoms, and indeed we do. We can actually pull out this vacuum polarization effect, we can calculate it, and we can measure it, we can compare it to what we get in the experiment, and we can see that it's physically there. So this is an excellent place to stop our discussion of the the introduction to quantum field theory, and for that matter, the course. So good luck with your studies, and I will see you another time. Bye.